Welcome to the deep dive. In our, well, pretty much on-command, on-demand world, information isn't just king anymore. It feels like the very air we breathe, digitally speaking.
It really does. Everything we do involves it.
Yeah, searching, sharing, connecting, using all those apps.
Yeah.
We're actually creating, more data as individuals than entire organizations used to. But
Hmm.
what happens when that invisible world of digital data falters?
Yeah. When your favorite app just grinds to a halt, that's the real challenge.
Exactly.
And our mission here at the Deep Dive is kind of to pull back that curtain. We take your sources, articles, research notes, whatever you've got, and we try to cut through the noise.
We want to extract those really important nuggets of knowledge and insight. Basically give you a shortcut to being genuinely well-informed without feeling, totally overwhelmed.
Precisely.
And today, we're doing just that. We're taking a crucial look under the hood, diving deep into the foundations of information storage and management, specifically how we actually design storage solutions for applications inside a data center.
Think of it like getting a peek at where all that digital stuff actually lives, and, maybe more importantly, how it's kept accessible and performing, especially under pressure.
Yeah, so we'll be walking you through the underlying principles and even a real-world scenario. Kind of like a couple of instructors guiding you through something complex, but honestly, pretty essential these days.
Okay, so let's start right at the beginning. What is data, fundamentally?
Good question. Where do we start?
Well, at its simplest, it's just a collection of raw facts. Think of a handwritten letter, maybe a printed book, or even just a photograph. They're the ingredients, from which we can draw conclusions.
Right. And what's fascinating is how that definition just exploded with the whole digital transformation. Before computers, data creation, sharing, it was pretty limited, right? Mostly paper, maybe film.
Mm-hmm.
Now, that same handwritten letter could be an email, that book an ebook, that photo, a digital image, a movie, and the wild part. It all boils down to binary numbers, just zeros and ones. Totally meaningless to us until a computer processes them.
That transformation is absolutely fundamental. And it wasn't an accident. This huge shift to digital, it was really driven by, three massive forces working together.
Okay, what were they?
First, the explosion in data processing power in modern computers. Suddenly, we had the muscle to turn almost anything into a digital format.
Right, we could actually handle it.
Exactly. Second, the cost of digital storage just plummeted. I mean, technology advanced, things got cheaper. What used to be super expensive became incredibly affordable. That just accelerated how much digital data we started generating and keeping.
Makes sense. More capacity, lower cost, leads to more data.
And third, the sheer affordability and, honestly, the lightning speed of communication tech. Remember sending a physical letter?
Oh, yeah. Days, maybe weeks.
Right. Now, an email gets halfway across the globe in, seconds? That instant communication dramatically cranked up the rate of digital data sharing.
And that leads us straight into this big data challenge we hear so much about.
Precisely. We're talking data sets so vast, so varied, changing so fast, that the normal software tools, they just can't capture it, store it, manage it, or even process it effectively anymore.
They're just overwhelmed.
Totally.
Yeah.
And this is exactly why we've seen this new discipline, data science, emerge. It's this powerful mix of stats, math, data visualization, and computer science.
So data scientists use fancy algorithms to sift through all this mess.
Essentially, yeah. They use advanced algorithms to find genuine business value hidden in these enormous piles of information. And that drives more informed decisions in, everything from medical research to real-time fraud detection. It's huge.
Okay, so we've got all this data flying around. Why do we need these, complicated storage devices then? Why not just keep it all on our laptops?
Well, it really boils down to one critical word: accessibility.
Accessibility, okay.
Whether it's your personal photos or a company's critical transaction records, data has to be stored so you can get to it easily, instantly, for more processing. Storage devices, from the little media card in your phone to these massive disk arrays in a data center, they're purpose-built for exactly that.
And the type of storage you choose depends on the data.
Yeah, it depends on the data type and how often you need to access it. Different tools for different jobs.
Got it. And for the really big players, the organizations dealing with truly massive amounts of data, it all kind of funnels into what we call a data center, right?
Exactly. Everything centralizes there. These aren't just big rooms full of computers either. They are incredibly sophisticated facilities designed to house and manage an organization's entire digital nervous system, basically.
So if you were to walk into a modern data center, what would you actually see? It sounds complex.
Oh, it is. It's a really complex ecosystem. On the hardware side, you've got racks packed with powerful computers, intricate storage systems, advanced network gear, and absolutely critical power backups to make sure things keep running.
Can't have the power go out.
Definitely not. Software-wise, you've got this deep stack of applications, operating systems, management software, kind of orchestrating everything. And don't forget the environment itself. Precise AC, fire suppression, ventilation, all keeping that high-tech gear happy and running 24/7.
Wow. Okay, so to really understand how it all works, you mentioned there are 5 core elements.
5 core elements, and the key thing is they're interdependent. They have to work together. First, you have the application. That's the actual program, like your online banking app doing the computing logic.
Okay, the app.
And the database management system, the DBMS. That gives you a structured way to store all the related data the app needs.
Right, like customer info, account balances.
Exactly. Third is the host, often called the compute platform. That's the actual machine, the server running the apps and the databases.
Got it. Host runs the apps and databases. What's next?
Fourth, the network. Think of this as the invisible data path, the superhighway connecting all these different devices and letting them talk.
The communication backbone.
Precisely. And finally, number 5 is the storage itself, the device where the data actually lives persistently. The hard drives, the SSDs.
So app, DBMS, host, network, storage. And you said they all have to work together.
Absolutely seamlessly. If even one link in that chain has a problem, the whole system can just grind to a halt. It's totally interdependent.
Can you give an example? How does that interaction play out?
Sure. Think about a simple online order. You place an order on a website, right? Your request goes from your computer, the client, to a host server running the order processing app.
Okay.
That app then talks to the DBMS on the host to get, say, inventory details or customer info. The DBMS then uses the host's operating system to actually write that new order data onto the physical disks in a storage array.
And the network connects all that.
Yeah, it's all connected by high-speed storage networks. It's like this complex, synchronized dance of information happening in milliseconds.
Okay, that paints a clearer picture. Now, within that data center, focusing on the storage system specifically, what are the absolute must-have characteristics? What makes or breaks them?
Great question. There are several key ones. First, absolutely top of the list is availability.
Making sure the data is there when you need it.
Exactly. And we're not talking minor inconvenience here.
Yeah.
For some industries like finance, downtime can cost millions of dollars per hour. So availability is non-negotiable.
Wow. Okay, availability is number 1. What else?
Then security. You need strong policies. And all the core elements have to be integrated to stop anyone unauthorized from getting in.
Makes sense. Keep the bad guys out.
Yep. Scalability is also crucial. Businesses grow, right? Their digital resources, including storage, have to grow with them smoothly without interrupting anything.
That you can add more storage easily.
Without disruption, yeah. And of course, performance. Every piece has to perform optimally, meeting whatever service levels the business needs. Slow storage can kill an application's usability.
Okay. Availability, security, scalability, performance. Anything else?
Yes, data integrity, super important. This is about making sure the data you store is the exact same data you get back later. We use clever things like error correction codes, parity bits to guarantee that.
So no corruption.
Right. You also need sufficient capacity. Enough space for all the data, obviously, but also the flexibility to add more or reallocate it without causing problems.
Right, you need headroom.
Definitely. And finally, manageability. You want easy, integrated management, ideally automated as much as possible, to cut down on manual work and potential errors. All these pieces have to click together perfectly.
That's a lot to juggle. Okay, shifting gears slightly. When you're first designing storage for a specific application, you mentioned understanding its I/O characteristics is crucial.
Absolutely. It's one of the first things you look at. You need to know. Is the app doing mostly reads or writes? Is it accessing data sequentially, like reading a file from start to finish?
Or randomly, like looking up one specific record in a giant database.
Exactly. And what's the typical size of those I/O operations, small chunks or big transfers? These patterns massively influence how the storage system performs and consequently how you should design it.
Okay, that makes total sense. So let's talk about the host then, the compute system itself. What's its role in this storage picture?
The hosts are the engines running your applications and your database management systems. They can be physical machines, traditional servers in a rack, or increasingly, they're virtual machines sharing the underlying hardware.
And what's inside a host, generally?
Well, you've got the core components, the CPU, the memory, various I/O devices. But just as important is the software stack working together. You've got the operating system, the file system, maybe a logical volume manager, and device drivers.
The operating system, the OS, that's like the main controller, right?
Exactly. It's the conductor. It controls all the computing, manages the hardware resources, and provides those essential data access services that applications rely on.
And what about device drivers? You mentioned those.
Yeah. Think of device drivers as the OS's translators. They're specialized bits of software that let the operating system talk to and control specific hardware devices. Like, it needs a driver to understand how to interact properly with a particular model of disk drive.
So the OS knows how to use the hardware.
Precisely. Then there's the logical volume manager, or LVM. These are often built right into modern operating systems, and they're fantastic tools.
Why are they fantastic? What do they do?
They provide optimized storage access, and they really simplify management. An LVM basically puts this clever abstraction layer between the OS and the physical disks. It hides all the messy details about where data physically resides.
Hides the complexity.
Yeah, which makes it surprisingly easy to do things like change storage allocation, even while an application is running. It's a huge help for engineers managing large, dynamic environments. Scaling and managing data becomes much, much easier.
Okay, so how does an LVM actually work its magic? What are the pieces?
It breaks down into three main parts. First, you have physical volumes, or PVs. These are your actual physical disks, or maybe partitions on those disks that the LVM knows about.
The raw disks.
Right. Then you group one or more PVs together into a volume group, or VG. Think of this like a big pool of available storage made up of those physical disks.
A pool of disks. Okay.
And finally, from within that VG pool, you carve out logical volumes, or LVs. You can think of an LV like a partition on a traditional drive, but way more flexible. And LV can actually span across multiple physical disks if needed.
So one logical volume could use space from several physical drives.
Exactly. Each physical volume is divided into these equal-sized chunks called physical extents. Logical volumes are just built from these extents. So yeah, an LV can easily span multiple PVs within the same volume group. This grouping of physical drives into one big logical volume is called concatenation. Very powerful.
Okay, so you've got these flexible logical volumes thanks to the LVM. What goes on top of that?
That's where the file system comes in. This is a hierarchical structure you're probably familiar with. Folders inside folders, files inside those. It's what makes it easy for us humans and for applications to find and access data stored on that underlying logical volume.
Right, it organizes everything, and it handles permissions too.
Yep, it controls how files are created, modified, deleted, accessed, and who has permission to do what.
And how is the actual file data stored within that file system?
Files themselves are stored in what are called file system blocks. These are the smallest chunks of storage that the file system allocates for data. A single file might use many blocks.
And can those blocks get scattered over time?
Oh, definitely. That's fragmentation. As files are created, grow, shrink, get deleted, the blocks making up a single file might end up scattered across the logical volume instead of being nice and contiguous.
Okay, so putting it all together, you've got the user, the application, the file system, the LVM, the physical disks. How does a file I save actually get mapped all the way down to the physical storage using an LVM? Walk me through that.
Sure, it's basically a 6-step process happening pretty much instantly behind the scenes. It's like this invisible bridge.
Okay, step one.
Step one, files are created and managed by users and applications. You hit save on your document.
Right.
Step two, these files reside within the file systems. That's where they get their name, their place in the folder structure, their permissions.
Okay, living in the file system.
Step three, the file systems map those files to file system blocks. Those basic storage units we just talked about.
File system blocks. Got it.
Step four, now the LVM starts its magic. Those file system blocks are mapped to the logical extents of a specific logical volume. Remember, the LV is that flexible partition we carved out.
Right, the LVM abstraction layer kicks in.
Exactly. Step five, these logical extents are then mapped by the OS or the LVM itself down to the disk's physical extents, so we're getting closer to the actual hardware.
Logical extents to physical extents.
Okay. And finally, step six. Those physical extents are mapped directly to the tiny disk sectors within the physical storage subsystem, the actual spots on the platter. So from you hitting save to the magnetic bits flipping on a disk, that's the journey.
Wow, that is quite a journey, happening all the time without us even noticing. Now, for that data to actually travel between the host and the storage device, we need some serious connectivity, right?
Absolutely. High-speed pathways are essential. We're talking to the interconnection between different hosts, or more relevant here, between a host and its storage devices.
And that involves physical parts and languages.
Pretty much. You need the physical components and the interface protocols, the languages they speak to each other. Physically, you've got the host interface device. That's often called a host bus adapter, or HBA, sometimes a network interface card, or NIC, depending on the type of connection.
What do HBAs do specifically?
HBAs are pretty specialized. They handle a lot of the I/O interface functions directly, which takes a load off the host's main CPU so it can focus on running the application.
Okay, so specialized cards. What else physical?
You also have the ports, which are just the specialized outlets on the HBA, and the storage device where you plug things in. And, of course, the cables themselves, the actual wires, which could be copper or fiber optic, connecting everything together.
Okay, HBA, port, cable, those are the physical pieces. What about the protocols, the languages they speak?
Right, the interface protocols are absolutely key. They define the rules for communication. Historically, for connecting internal storage like disk drives or CD-ROMs in PCs, IDIATA was really common.
I remember ID cables, big flat ribbons.
Exactly. That was parallel ATA, or PATA. It evolved into serial ATA, or SATA, which is much faster and uses smaller cables. SATA 3.0, for instance, can hit speeds up to 6 gigabits per second. Pretty standard in PCs today.
Okay, so SATA for desktops mainly. What about servers?
For higher-end servers and workstations, SESI became the preferred choice for a long time. It offered better performance, scalability, could connect more devices, and better compatibility overall.
SCSI.
Yep. It also evolved into a serial version called Serial Attached SCSI, or SAS, which is still a major workhorse in data centers today. It supports lots of devices, good speeds.
And is there anything even faster for the really demanding stuff?
Oh yes, for the highest speeds and most demanding enterprise environments, Fiber Channel, or FC, is typically the king. It's basically a gigabit speed network protocol designed specifically for storage traffic.
Fiber channel uses fiber optics.
Often, yes, especially for longer distances, but it can run over copper too. It uses serial data transmission, and the latest versions, like 16FC, can hit speeds of 16 gigabits per second.
Wow, 16 gigabits per second. That's incredibly fast.
It is. Think about downloading a full HD movie in like less than a second. That's the kind of speed you need for the massive data pipelines in modern data centers.
Okay, so we've got the components, the connections, the languages. Now let's zoom in on where the data actually lives, the storage media itself.
Right. Broadly, we can categorize it into magnetic media, like your traditional hard disks and, historically, tapes. Then there's optical media, like CDs and DVDs. And the newer kid on the block, solid-state media, like flash drives or SSDs.
Let's quickly touch on tapes and optical. Are they still relevant in data centers?
Well, magnetic tapes used to be huge for backups, but they had big drawbacks. Access was sequential. You had to wind through the tape to find data.
Like an old cassette tape.
Exactly. Plus, the read-write head physically touched the tape, causing wear and tear. And managing large tape libraries was a major headache. With disk prices dropping so much, tapes aren't really the go-to for primary enterprise backup anymore, though some use them for long-term archive.
Okay, so tapes are mostly out for active use. What about CDs and DVDs?
Optical disks. Great for distributing software or maybe personal backups. But for serious business applications, their capacity and speed are just too limited. Their main advantage is being worm. Write once, read many.
Meaning you can't change the data once it's written.
Correct. That makes them useful for things like legal archives, where you need proof the data hasn't been tampered with. But it's a pretty niche use case in the grand scheme of things.
So that really leaves us with magnetic disks and solid state.
Pretty much, for the bulk of active data center storage, the absolute workhorse for decades has been the disk drive, the hard disk drive, or HDD.
Why have they been so popular?
They're still the go-to for many performance-intensive online applications, mainly because they offer a great balance. They support rapid random access to data, which is crucial for databases, and they offer enormous capacity for a relatively low cost per gigabyte.
And you usually see lots of them together.
Almost always. They're configured in arrays, basically groups of disks working together to boost both capacity and overall performance.
Okay, so HDDs are the workhorse, but then there's the new generation, right? Flash drives.
Right, the flash drive or solid-state drive SSD. These are the real game changers. They use semiconductor memory like the RAM in your computer, but persistent. The key thing, no moving parts.
No spinning platters, no moving heads.
None. And that translates directly into ultra-high performance, incredible speed, and much lower power consumption compared to HDDs.
Where do they really shine?
They absolutely excel in workloads that involve lots of small, random reads where you need lightning-fast response times. Think of things like high-frequency trading systems or busy database index lookups.
But they're more expensive, right, per gigabyte?
They are, yes. The cost per gigabyte is still higher than HDDs. However, because they're so much faster, you often need far fewer SSDs to achieve the same level of performance as you'd get from a larger number of HDDs. So the total cost of ownership, the TCO, can actually be better with SSDs in many cases.
Interesting. So it's not just about the purchase price. Okay, let's dive deeper into the traditional HDD then, since they're still so common. To really get a disk performance, we need to understand the components, right?
Absolutely. Let's dissect the HDD. At its very heart is the platter. This is a circular disk, usually made of aluminum or glass, coated with a very thin layer of magnetic material. That's where the Z's and 1s are actually recorded as tiny magnetic spots.
And there are usually several platters stacked up.
Typically, yes. Multiple platters are stacked on a central spindle. This spindle connects all the platters and rotates them at a constant, very high speed. We're talking anywhere from, say, 5,400 revolutions per minute RPM in basic drives, up to a screaming 15,000 RPM in high-performance enterprise drives.
Okay, spinning platters. What reads and writes the data?
That's the job of the read-write head, often just called the RW head. There's usually one head for each platter surface. It's attached to an actuator arm that moves it across the spinning platter.
And it actually touches the platter.
No. That's the amazing part. It flies incredibly close, hovering on a microscopic cushion of air generated by the spinning platter. This gap is called the head flying height, and it's thinner than a smoke particle.
Wow. So what happens if it does touch?
That's the dreaded head crash. If the head makes contact with the platter surface while it's spinning fast outside of its designated landing zone where it rests when powered off, it can scrape off the magnetic coating. That almost always means catastrophic data loss for that area, potentially destroying the drive.
Yikes. Okay, so keep the heads flying. Now, when we talk about HDD performance, what are the critical factors? What makes one drive faster than another?
There are three main mechanical factors that dictate speed. First is seek time, which is sometimes called access time. This is literally the time it takes for the actuator arm to physically move the RW heads across the platter to get to the correct track, the correct concentric circle where the data resides.
So it's a physical movement time, measured in
Milliseconds process. And the faster the seek time, the quicker you can start accessing data, especially random data scattered across the disk. Drive vendors usually quote a few types of seek time. There is full stroke, which is the time to move the head all the way from the innermost track to the outermost, vice versa. There's average seek time, which is statistically the time for about 1/3 of a full stroke. This is the most commonly quoted spec, typically somewhere between 3 and 15 milliseconds for modern drives. And then track-to-track seek time, which is just the time to move between adjacent tracks, very quick.
Okay. And you mentioned something called short stroking.
Yeah, that's an advanced technique to minimize seek time for very performance-sensitive applications. Engineers can configure the drive to only use a small subset of the available cylinders, usually the outer, faster ones. This drastically reduces the distance the head has to travel.
But you lose capacity doing that.
Big time. You sacrifice a lot of usable capacity to get that seek time improvement. It's a trade-off.
Okay, so seek time is positioning the head over the right track. What's next?
Next up is rotational latency. Once the head is sitting over the correct track, you still have to wait for the platter to spin around, so the specific sector containing the data you want is directly underneath the RW head.
Ah, the waiting time for the disk to spin.
Exactly. And how long you wait depends entirely on the spindle speed, the RPM. Faster RPM means less waiting time. For example, on a fast 15,000 RPM drive, the average rotational latency is only about 2 milliseconds. For a 7,200 RPM drive, it's longer, maybe around 4 milliseconds. It's a significant factor in the total access time.
Okay, seek time to get to the track, rotational latency to get to the data on the track. What's the third factor?
The third is the data transfer rate, often just called the transfer rate. This is the actual speed at which data can be read from the platter and sent back to the host or written to the platter. It's usually measured in megabytes per second, MBs, or gigabytes per second, GBs.
And is there just one transfer rate number?
Not quite. There's the internal transfer rate. This is the speed data moves directly off the platter surface into the disk drive's internal buffer or cache memory. This rate is affected by factors like how densely the data is packed on the platter.
Okay, speed off the physical media.
Right. Then there's the external transfer rate, sometimes called the interface rate. This is the speed at which data can move between the drive's buffer and the host bus adapter through the interface like SATA or SAS. This is often the speed advertised on the box, like SATA 6 Freemans.
But you don't always get that full speed.
Almost never sustained. The interface speed is the theoretical maximum of the pipe. The sustained external transfer rate, what you actually experience when moving large files, is usually lower because it's ultimately limited by how fast the drive can actually read-write data internally and handle the mechanics.
Okay, that makes sense. Seek time, rotational latency, transfer rate, those determine the raw speed. Now let's connect this to the applications experience. You talked about I/O controller utilization. How does that impact things?
This is absolutely critical. You can sort of visualize a disk drive from the host perspective as a black box. Inside that box, there's a queue where incoming I/O requests from the host have to wait if the drive is busy. And there's the I/O controller itself, the drive's internal brain, which processes those requests one by one from the queue.
So requests might have to wait in line.
Exactly. And the factors affecting the overall response time, how long it takes from the moment the host sends an I/O request until it gets the response back, are directly linked to this. It depends on how fast I/O requests are arriving, the arrival rate, how long that queue gets, and of course the actual time it takes for the I/O controller to process each individual request once it gets to the front of the queue.
So if requests arrive faster than the controller can handle them?
The queue grows longer and longer, and your response time goes up, potentially way up.
Is there a way to model this?
Yeah, there's a fundamental queuing theory formula that captures the relationship. Average response time, service time, 1 utilization.
Okay, break that down. Service time, utilization.
Service time is the average time the controller takes to actually process one I/O request, assuming no waiting in the queue. It includes the seek time, rotational latency, and data transfer time we just discussed. Utilization is simply how busy the controller is, expressed as a fraction between 0 and 1, or 0% to 100%.
Okay, service time divided by 1 minus utilization. What does that tell us?
It tells us something crucial, what we call the bottleneck effect. Look at the formula. As utilization gets closer and closer to 1, or 100%, the denominator, 1 utilization, gets closer and closer to 0.
And dividing by a number close to 0 gives you
A huge number. The response time approaches infinity. It doesn't just increase linearly, it skyrockets. When a component like the disk controller becomes saturated, close to 100% busy, it forces I/O requests to be processed strictly one after another serialization. Everything just piles up waiting.
That sounds bad, like a massive traffic jam.
It's exactly like that. Which brings us to a really important rule of thumb in storage design, the 70% rule.
The 70% rule. Okay, what's that?
If you plot a graph of disk utilization versus response time, it's not a straight line. It's a curve that starts fairly flat but then bends upward sharply. Response time starts increasing exponentially once utilization goes much beyond 70%.
So keep utilization below 70%.
For any application that cares about performance and predictable response times, absolutely. You need to design the storage system so that the disks, at peak load, are operating below 70% of their maximum I/O serving capability. Pushing them harder is just asking for trouble. Inconsistent performance, timeouts, unhappy users.
Right. Ignoring that rule is like driving your car with the pedal slammed to the floor constantly. Something's going to break.
Exactly. It's a recipe for disaster in production systems.
Okay, that 70% rule is crucial. So with that foundation, let's get into the practical methodology. How do we actually figure out the storage requirements for a given application? Where do we start?
It always starts with figuring out 2 key things. How much storage capacity the application needs, and what kind of I/O performance it requires.
Capacity seems like the easier part.
Generally, yes. Estimating capacity is relatively straightforward. You look at the size and number of file systems, database components, log files, etc., that the application will use, maybe add some buffer for growth.
Okay, capacity is mostly addition. What about performance?
Performance estimation is definitely more complex. It involves really understanding the application's workload. The typical I/O size, the mix of random versus sequential access, the read versus write ratio, and critically, the number of I/Os per second, IOPS, the application will generate during its busiest periods, its peak workload.
IOPS, input-output operations per second. That's the key performance metric.
A very common and important one, yes. And to figure out how many disks you need to meet that IOPS requirement, you first need to know the performance capability of a single disk. A key measure here is the disk service time, TS we touched on earlier.
Right, the time the disk takes to handle one I/O. That was seek time plus rotational latency plus transfer time.
Precisely. Seek time plus rotational latency plus data transfer time. And the transfer time part depends on the size of the I/O block being transferred and the disk's data transfer rate. For instance, if you have a 32 kilobyte I/O and the disk's transfer rate is 40 megabytes per second, you can calculate how long that transfer portion takes.
Okay, so you calculate the service time TS for a typical I/O on that specific disk model. What then?
Once you have the average service time, TS, in seconds, you can calculate the theoretical maximum IOPS that single disk could possibly handle. It's simply 1 divided by TS. So if the service time is, say, 0.01 seconds, 10 milliseconds, the maximum IOPS is 1.01 equals 100 IOPS.
But that's at 100% utilization, right? Which we just said is bad.
Exactly. That maximum IOPS number assumes the disk controller is busy 100% of the time, which leads to terrible response times. So while it tells you the absolute ceiling, you cannot use that number directly for designing systems that need good performance. You have to apply the 70% rule, or maybe even a stricter one depending on the application sensitivity.
Right, so the usable IOPS per disk is significantly lower than the theoretical max.
Much lower, yes.
Got it.
Which leads us to the governing principle for figuring out the total number of disks you need. The total number required is always the maximum of these two calculations. The number of disks needed just to meet the capacity requirement, or the number of disks needed to meet the performance IOPS requirement, calculated using that safe utilization level like 70%.
So you calculate both and take the bigger number.
Exactly. You might need only 5 disks for capacity, but if you need 20 disks to handle the IOPS load safely, then you need 20 disks overall. Performance often drives the disk count higher than capacity does, especially for transaction-heavy applications.
Okay, this is making sense. Let's walk through that practical example from the source material to really nail it down. What was the scenario again?
Right, the example scenario was an application needs 1.46 terabytes of usable storage capacity, and at its peak workload, it's expected to generate 9,000 IOPS.
Okay, 1.46 TB capacity, 9,000 IOPS peak load, and what kind of disks did they have available?
The vendor specified they were using 146 GB at capacity, 15,000 ROPM drive.
Yeah.
And crucially, the vendor stated this drive model is capable of a maximum of 180 IOPS.
Okay, 146 GB, 15K RPM, 180 max IOPS per drive. Step 1, calculate for capacity.
Yep, that's the easy one. The required capacity is 1.46 TBB, which is 1,460 gigabits. Each disk holds 146 GB, so 1460 gigabits divided by 146 GB disk equals 10 disks. Purely for capacity, you need 10 disks.
Simple enough. Step 2, calculate for performance, but using the maximum IOPS first, just to see.
Right. The application needs 9,000 IOPS total. Each disk can theoretically do a maximum of 180 IOPS. So 9,000 IOPS divided by 180 IOPS disk equals 50 disks.
Okay, so 10 disks for capacity, 50 disks for raw maximum performance. But now we need step 3. Apply the 70% rule because this application likely needs good response time.
Exactly. We can't run those disks at 100%, 180 IOPS. We need to derate them to a safe utilization level. Let's use 70%. So the realistic sustainable IOPS per disk is 180 IOPS disk 0.70, which equals 126 IOPS per disk.
126 usable IOPS per disk. Now recalculate the number of disks needed for performance using that safer number.
Application needs 9,000 IOPS. Each disk can safely deliver 126 IOPS. So 9,000 IOPS divided by 126 IOPS disk equals 71.42 disks.
And you can't have 0.42 of a disk.
Nope. So you always round up to the next whole number. That means we need 72 disks to meet the performance requirements safely.
Okay, so step 4 is the final determination. Compare the capacity need, 10 disks, with the safely calculated performance need, 72 disks, and take the maximum.
Right. Max 10 disks, 72 disks equals 72 disks. That's the final answer. You need to install 72 of those drives to satisfy both the capacity and the performance requirements of this application, ensuring good response times by keeping utilization under control.
And that really highlights how performance demands, the IOPS, often dictate the solution far more than just the raw storage space needed. 72 disks versus just 10 for capacity.
It's a very common outcome, absolutely. And, it's worth mentioning quickly that in real-world data centers, engineers use other tricks to help optimize this. Things like RAID configurations for protection and performance, large cache memory and storage controllers, maybe using those super fast flash drives we talked about, or features like native command queuing in the drives themselves. These can all help reduce the raw number of spindles needed, especially for performance.
Right, there are more advanced techniques. But this basic calculation methodology, capacity versus safe performance IOPS, is the fundamental starting point.
It absolutely is. Understanding this trade-off is key.
Okay, great walkthrough. So that brings us to your turn. We've laid out the concepts, the components, the calculations, the crucial 70% rule. Now let's give you, our listener, a chance to apply it.
Yeah, let's look at a concrete scenario, a challenge we'll call Lab 1, designing a storage solution for an application. Imagine an organization is planning to roll out a new, very important business-critical application.
Okay, new critical app. What are its requirements?
Here's what we know. First, it needs 1 terabyte TB of usable storage space for all its business and application data.
1 TB capacity. Got it. What about performance?
During its peak workload times, it's expected to generate 4,900 IOPS. And the typical I/O size for these operations is 4 kilobytes, KB.
Okay, 4900 IOPS, 4 KB I/O size. And because it's business critical?
Exactly. Because it's business critical, the response time absolutely must be kept within an acceptable range. That's a key constraint. Think 70% rule.
Right. That implies we can't push the disks too hard. So what hardware do they have to work with?
For this lab, they have a specific disk drive model available. It's a 15,000 RPM drive, and each drive has a usable capacity of 100 gigabytes, GB.
100 gigabytes, 15K RPM. Do we know anything else about its performance?
Yes, 2 more crucial specs for this specific drive model. The average seek time is 5 milliseconds, MBMs, and the data transfer rate is 40 megabytes per second.
MBAs. Correct. 100 gigabyte capacity, 15K RPM, 5 meters average SIG, 40 millibytes transfer rate. Application needs 1 TB capacity, 4900 IOPS at 4 KB, and good response time.
So the task for you is this. Based on everything we've just gone through, calculating service time, figuring out maximum IOPS, applying that crucial utilization rule, and balancing capacity versus performance, how would you determine the minimum required number of these specific disk drives to meet all the needs for this application?
It's a perfect chance to put these principles into practice, just like a storage architect would need to do in a real-world design situation.
Exactly. Think through the steps we discussed.
Okay, so today we've really journeyed through the quite intricate world of data storage. We started with, what data even is, looked at the components inside a hard drive, and unpacked those crucial factors like seek time and latency that dictate performance.
Then we broke down the methodology for calculating storage requirements, walking through that detailed example showing how capacity needs and performance needs interact, and how performance often drives the final design, especially when you factor in response time using that 70% rule.
And we wrapped up by presenting you with that Lab 1 challenge, letting you apply these very principles to a realistic design problem.
And understanding these underlying mechanics, the physics and logic of storage, it's still absolutely essential. Even as storage gets more abstracted with things like virtualization and cloud computing, these fundamental principles we talked about today, they're still the bedrock everything else is built on.
They really are. You can't escape the physics entirely. Which leads to a final thought to leave you with. As we keep seeing modern applications demanding ever higher performance, needing insane IOPS, what do you think might be the next major leap in storage technology?
Yeah, something beyond even today's fast flash drives. What could come along that completely redefines how we calculate and provision storage for these extreme IOPS requirements? What's on the horizon that can make even current SSDs seem, well, slow?
Something to ponder. What does that future look like? We'll leave you with that until our next deep dive.